In this example, we're going to look at calculating the equilibrium composition for the water-gas shift reaction, where we feed carbon dioxide and water to make hydrogen and carbon dioxide. We're going to look at carrying out the calculation by using extent of reaction and equilibrium constant, and we're going to compare that to using Gibbs minimization. And this calculation, we're going to use temperature-dependent heat capacities and also heats of formation, which allow us to calculate, of course, heat of reaction that are also a function of temperature. So let's first look at the extent of reaction calculation. So the idea is we have the reaction of carbon dioxide and water to make hydrogen and CO2. In this particular example, we're starting with 2 moles of CO, 2 moles of water, and initially 0 moles of the products. And then, so this is moles, and then here's equilibrium moles. So we use the extent of reaction. And so the equilibrium constant, we get, if we assume ideal gases, it's the ratio of partial pressures. And so pressure of hydrogen, pressure of products, pressure of reactants. Now partial pressures we can write in terms of mole fractions, independent of the total pressure since there's no mole change. So I could write this in terms of mole fraction of hydrogen, mole fraction CO2, and mole fraction of the 2 reactants. And because there's no mole change, this is also the number of moles of hydrogen, number of moles of CO2. And so to carry out the calculation, since I can write the number of moles in terms of extent of reaction, I need the delta G of reaction so I can calculate the equilibrium constant. So what we've done, and done this on a spreadsheet, first we calculate delta H of reaction at standard conditions as a function of temperature. And that allows us to calculate delta G of reaction, standard conditions, and 750 Kelvin. Again, we calculate this using heat reaction as a function of temperature and heat capacities for function of temperature. And the value for delta G of reaction is minus 11.21 kilojoules per mole. Well, this then allows us to calculate equilibrium constant, which is the exponential of minus delta G of reaction, temperature over RT. If I substitute the numbers in, equilibrium constant, so that means I can substitute for K equilibrium in this equation and write this in terms of the extensive reaction. So equilibrium constant on the left side, extensive reaction, 2 products. Well, this I can take the square root of to solve, so the extent over 2 minus the extent, then the square root of 6.038, which means I can solve for the extent. And so the extent of reaction, this is in terms of moles. Well, I can use this, substitute back into our equilibrium moles, and calculate the number of moles. So let me, at equilibrium, so let me just pause and write those numbers down. So here are the results of using the equilibrium constant and extent of reaction. So let's compare this to the approach using Gibbs minimization. So this approach doesn't have advantages when we just have one reaction, where it has the real advantages when we have multiple reactions, but we're going to look at it for the simpler case to make it a little easier to understand. And so the idea is what we're going to minimize is the number of moles times the Gibbs free energy per mole for the mixture. And I'm going to write this in terms of the terms. So it's the number of moles of each component. Of course, that's at equilibrium, that where we get the minimum. And so the standard state Gibbs free energy of formation for each component at the temperature of equilibrium divided by RT plus the log of the mole fraction times the pressure. So that's what we're minimizing. The big advantage of Gibbs minimization, we don't actually specify what reaction is taking place. When that becomes valuable is when we have 3 and 4 reactions. So in addition to that minimization, we have to have atomic mass balances, meaning the number of carbon atoms at the start into our, say, reactor system is the number of carbon atoms at the outlet. And likewise for oxygen and hydrogen. So then what we're going to do is use Solver in Excel to minimize this with these 3 equations as constraints. Now, we've already assumed ideal gases when we've written the equation here in terms of just mole fraction. Our initial guess can affect convergence, and one of the other constraints we're going to put on is that the number of moles should be a positive number. Now, the way to do that in solvers for each of the number of moles, I'm going to say it's greater than 10 to the minus 12. Well, let's look at the results, and then we'll look at the spreadsheet. Well, here are the results copied from the spreadsheet. Approach using Gibbs minimization versus using equilibrium constant. You see we get the exact same answer, which of course is encouraging, a good check that the spreadsheet is behaving correctly. And let's just briefly look at that spreadsheet. So let me mention, so that it's possible to study it in a little more detail, the spreadsheet is located at the LearnChemE website, learncheme.com. So briefly describe it, and another screencast will go through this type of spreadsheet in more detail. But the idea is we have the number of moles coming in, and we make guesses initially at the number of moles leaving, and then we're minimizing this cell that's in yellow using solver, and we have the constraints, which you can see are satisfied, that the number of moles of carbon coming in equals the number of moles of carbon coming out. Likewise for hydrogen and oxygen. Well, the rest of the spreadsheet has the heat capacities that allow us to calculate delta H as a function of temperature and calculate delta G. The delta G's then are in column E. These are delta G's of formation for each of the components at standard conditions. The minimization, you can see again, this is in cell J8. See, we're looking at the delta G of formation at standard conditions divided by RT, and this log mole fraction times pressure. Well, for this reaction, pressure is not going to change anything because 2 moles react to 2 moles. So the same answer would be obtained if we were at 10 bar pressure, for example, assuming still ideal gases. The result of this calculation agrees exactly with the extended reaction. And keep in mind, the real advantage of this is now we can add another molecule to this list and calculate a new equilibrium without having to specify what reaction was involved to make that molecule. Or we could add 4 more molecules. Calculation would be essentially identical, and not much more effort than this, where it's much more calculation effort when we have 4 extensive reaction, for example.